So thank you very much for the invitation, for the presentation also. And so my aim today is to speak about a joint work with Thomas Brüstle and Eric Hanson on invariants for poset representation. So this is a work still in progress. So let me start with the setting. So I start with any field K, and I start with a finite poset. So typically you have to think that this is, for instance, a two-dimensional grid like this. And I'm interested in a finite dimensional K representation of this poset P that I denote by mod P. And also I will denote by int P the set of isoclasses of indecomposable representation of P. And the aim is really comes from persistent theory. And well, I could like an aim in persistent theory would be to classify representation of P, which is of course a non really reasonable aim, because most of finite posets they are white representation type. So there is no hope to classify the representation of P, but still what I mean by classify is to find good invariants to classify this representation of P. But of course, this invariant won't be complete in the sense that they won't distinguish all indecomposable representation of P. But so let me start with the definition, which is quite natural. So a Z linear invariant is a morphism of abelian groups. So phi from K0 split of P into some abelian group of finite rank. So with, I will be a finite set because I want to be able to compute this. So I am aiming to end up in something of finite rank. And here, what I mean by K0 split, so this is a split Grothendieck group of mod P. So in fact, this is just a function that assigned to any indecomposable module over P an integer and which is additive. So the first very basic example is a dimension vector. So the dimension vector is just a function that associates to any module M the dimension of MP, where P runs over all the vertices of my poset P. And this is, of course, a morphism of abelian groups. The second example, which is very classical in persistent theory, is a rank invariant. And the rank invariant assigned to, so it goes first to Z to this set. So I just consider the set of pairs of element in P such that A is smaller or equal to B. And I assign to M the rank of the map going from MA to MB, where AB belongs to this set. And this is, this is another kind of invariant here. And the idea what would be to generalize these invariants. So first, in order to study these invariants, we have to be able to compare them. And so I will set two definitions here. So the first one is, so I start with two invariants, phi1 and phi2. And I will say that phi1 is finer than phi2 if there exists a D linear map going from the image of phi1 to the image of phi2 such that the composition is phi composed with phi1 is equal to phi2. So here, just a remark, I don't ask my invariant to be surjective. So in general, it's not surjective on all this set. So that's why I really ask to compare the image as a subgroup of this ZI1 and ZI2. Okay, and so my other definition will be that phi1 is equivalent to phi2 if there exists such a phi, but I ask phi to be an isomorphism of abelian group. So an isomorphism of abelian groups phi. So with the same definition, so phi1 to phi2 such that the composition of phi with phi1 is phi2. And then it's very easy to, as a first example, to compare the two invariants I presented in the first part, that the rank is finer than the dimension vector. So in other words, if you know the rank, you can deduce the dimension vector, of course, because just by taking here, you take A equals B, and of course, this rank will be just the dimension of MA. And so you have, so this notion of being finer is really like you have more information knowing phi1 than knowing phi2. Okay, so now I will start with a new definition. And so I will say that I will say that a phi basis is a subset of indecomposable module such that if I restrict phi to the subset of M, the subgroup generated by the element in the basis, is an isomorphism of abelian group. And typically my example will be first, so if I take the dimension, I can consider the simples. The simples module, they will form a dim basis. And the other example comes from Botman, Opperman, Udo, and I can take the rectangle, and the rectangle will form a rank basis. And here, typically the rank basis, the rectangle basis, sorry, is given by, so if you think, so I take A and B here, and a rectangle will be a module which is supported by all this rectangle here. So in other words, RAB X is K if and 0 else. Okay, so these are two examples. And now I will come to the new definition. So I start with two posets, and I will call a map from X to P, an order embedding. If the map F from X to the image of F is an isomorphism of poset, and I will denote by E the set of all order embeddings. And just first remark is just that given an F, I will get a restriction functor F star, which is exact and which has left and right adjoint. And now I can define a new invariant. So I take I to be the indecomposable set of X, and my new invariant is modX, and that assign to M the multiplicity of X of any, I take any indecomposable U, and I take F star of M. So F star of M is a representation of X, and I just compute the multiplicity of the indecomposable U in the F star of M. And just to illustrate this by example, so if I take X to be 1, so I just end up with a dimension vector again. And if I take X to be just this poset with 2 elements, I get something which is equivalent to the rank invariant, not completely the rank invariant, because in that case, this is not surjective. And sorry, I'm a bit late. And now I'm just, yeah. And if I take a new poset, like this poset, then I get something which is in general strictly greater than the rank. And I will finish by giving you a theorem that saying that you have a basis which is the sort of rectangle basis. So for each f, I define some module, which is defined like this. So which is typically a sort of rectangle module like this, which is supported like this. And what we prove together with Thomas and Eric is that rectangles plus this theta f, they form a multi-x basis. And yeah, okay, maybe I will just stop here. Thank you, and sorry for the small delay.